Hello students, it's Dr. Sansom, and today I would like to talk about electron configuration. So I'm going to be talking about sort of three things at the same time. One thing I'm going to be talking about is orbital diagrams. That's what this thing is over here. I'm also going to be talking about electron configurations. I'm going to write those over here on the right. And I'm also going to be talking about the way the periodic table is organized. So I'm going to be coming in here and looking at the periodic table too. Okay, so I think the orbital diagram is the best place to start here. I'm going to be starting to fill in electrons. So this is like an atom that doesn't have any electrons in it, and I'm going to start filling in the electrons. So the first question is, where do I fill in the electrons? Well, I'm going to start at the bottom, and I'm going to put an electron in here. We usually use arrows to represent the electrons. This one is pointing up, so that's like an up spin or an m sub s value of plus 1/2. And I started at the bottom because of something called the Aufbau principle, which is that you should start filling in electrons from the lowest energy available, and then once that energy level is full, you can go up to the next energy level. So that's the Aufbau principle. So I've written one little arrow inside of my 1s orbital diagram. This is actually the electron configuration for hydrogen, and we write 1s1 because inside my 1s orbital I have one electron. Now if we look at the periodic table, on the periodic table, in the first period or row of the periodic table, this is hydrogen right here. And it's in the first period or row on the periodic table, and it's in the S block. That is like our S1S, first row, S block. And it's in the first column of the S block. And that is how we get our 1s1. Okay, that's 1s1, hydrogen. Next one is helium. Helium is 1s2. Now, when I put my electron in this orbital, there's another rule that I need to be aware of. It's the Pauli exclusion principle. The Pauli exclusion principle says that no two electrons can have all of the same quantum numbers. And so when I put that second electron in the same orbital, it has to have the opposite spin. That's why I drew the arrow going down. Now I have two electrons in my 1s orbital, so my electron configuration is just 1s2. And if I look at the periodic table, on the periodic table, I'm in the first period. I'm in the S block. Helium also makes up part of the S block. Helium is here in the S block. It's in the first row of the S block and in the second column. So that's my 1, which is my period, my S, which is the block, and then my 2, which is the column number, 1s2. So I get 1s2 for helium. Next, I have lithium. Lithium is 1s2, 2s1. Now, I've filled up my 1s energy level, so I'm going to go to my 2s energy level and put my electron there. If I look at lithium on the periodic table, I'll notice that it's in the second period and the S block and in the first column of the S block. So that's going to be my 2s1. And my electron configuration ends in 2s1. Okay, after lithium, we have beryllium. We're going to add another electron, 1s2, 2s2. My second electron goes in, nothing fancy. If I look at the periodic table, I find beryllium here in the second period, in the S block, and in the second column. That's my 2s2. Okay, next one, I have boron. Now I'm going to put my first electron into the 2p. So I'll have 1s2, 2s2, 2p1. And I'm going to put that electron right here. Still following all the same rules. As I've gone along, I started at the bottom, I'm working my way up. I'm filling up the energy levels before I go on to the next one. Everything is working fine. If I look at beryllium on the periodic table, boron on the periodic table, then I notice it's the second period. It's in the P block, and it's in the first column of the P block. That's my 2p1. that I have here in my electron configuration. Okay, after boron, I have carbon. Now carbon is going to be 1s2, 2s2, 2p2. And this is where there is a choice about where the electron could go. It could go in its own orbital, like if I drew it here, or I could put it in this orbital with the other one just facing down, like I did with the ones that came before it. How do I decide which one to do? Well, I'm going to follow Hund's rule, H-U-N-D, Hund's rule. And this rule says that electrons are going to fill singly in orbitals of equal energy until they're forced to pair. So I've got one electron there. I'm going to put my next electron in its own orbital. It's filling singly, not paired, until it doesn't have any choices. The reason is if they're paired, there is some electron-electron repulsion. There's an energetic cost to that. So it's more stable, or there's lower in energy to put the electron in its own orbital if we have a choice about that. Now, if I look at my periodic table and I look for carbon, it's in the second period, it's in the P block, it's in the second column of the P block. That is my 2p2. Okay, after carbon, I get nitrogen, which is 1s2, 2s2, 2p3. I add my third electron here. If I look at nitrogen on the periodic table, it's the third column. So second row, which is my 2, P block, which is my P, and third column, which is my 3, 2p3. After nitrogen, oxygen, 1s2, 2s2, 2p4. I put my fourth electron. This one comes back to the beginning and gets paired. There were no more free orbitals in that same energy level. So the best thing to do then is to pair up. So that is my 2p4. And oxygen on the periodic table is in the fourth column of the P block. We can finish this out with fluorine, 1s2, 2s2, 2p5, and neon, 1s2, 2s2, 2p6. Notice neon now, the entire second energy level is totally full of electrons, so that we say it has a completed or a full shell, and that makes neon particularly stable. So that's an introduction to how we write electron configurations using the periodic table. There's one additional thing that I want to point out. We only did up through the second period here, but let's say I wanted to do something like vanadium. Vanadium's my favorite element. Vanadium here is in the D block. And if we go back to our energy levels, you might notice here that 4s is actually lower in energy than 3d. And this is reflected on the periodic table. If we follow along across this first row, we go 1s2, we go 2s2, 2p6, 3s2, 3p6. We're at the end though, and we didn't get to the 3d. Where does it come? Well, I follow along 4s2, and then this will be the 3d. It comes after 4s. So if I'm writing my electron configuration for vanadium, I can write argon, which is the noble gas that comes before it, and then 4s2, 3d3. And I point this out because the D's are actually shifted down one row because of the energy, where when we fill the electrons, the 3d orbitals are higher in energy here than the 4s. Okay, that's the end of our electron configurations. I hope that's helpful.